So we were discussing this particular rule. The rule states that the breakaway points, that means the points at which the characteristic equation of the system will have multiple roots. So breakaway points can be found by solving this equation dk ds equal to 0. So if you solve this equation, then the roots of this particular equation will give us the information regarding the breakaway point or points of the system for which we are trying to sketch the root locus, right? Now we discuss this particular example. Here, this is the characteristic equation 1 plus k into, can you see the material? Is it legible?
Yes, ma'am.
Okay. 1 plus k into 1 by s into s plus 1 into s plus 2. So from this equation can be represented as k by s into s plus 1 into s plus 2 equal to minus 1. And from that we can express k as a function of s, and k will be given by k is equal to minus s into s plus 1 into s plus 2. So if we can express k as a function of s, then we can take the first derivative of k, and we can form that equation, and we can solve the equation for finding out the roots of the characteristic equation. Sorry. We can find the roots of that particular equation, and from that we can find out the locations of the breakaway points of the system. Uh, could you please sketch this part of the locus, or rather, just very fast, quickly sketch this particular locus. A rough sketch will do. Done. Done. Should I continue?
Yes, ma'am.
So let's take that particular example. So k is equal to, as you can see, minus s into s plus 1 into s plus 2. So from that we have obtained this equation, and after that we have taken the first derivative of k with respect to s. So this is a third order equation, so we'll get a second order one. So it's given by 3s square plus 6s plus 2 equal to 0, right? And if we solve that equation, we'll get two roots of this particular equation, dk ds equal to 0. And if you solve, it's your assignment, please check the values. I'm not sure whether the values are correct or not. So the roots, as shown in this book, are located at is equal to minus 0.423, and the second root of this equation is minus 1.577. Right? Now, look at the root locus once again. So intuitively, we can sketch the root locus without knowing the exact location of the breakaway point, but it's clear that this is one onlooker segment, and this is the third onlooker segment. Already we have discussed this locus, right? So one root branch will originate from this open loop pole, the second root branch will originate from this open loop pole, this root branch will move along this direction, this one will move along this direction. So on this particular onlooker segment, at a particular point, two real root branches will meet, and after that, if we increase the value of gain k beyond this particular value, then these two real root branches will form two complex conjugate root branches, and these two root branches will tend towards infinity along these two straight line asymptotes, and the third root branch will originate from minus 2, and it will tend towards infinity along the negative real axis, right? So it's apparent that this particular system for this particular system will have one single breakaway point and located on this particular segment. You get my point,
Yes, ma'am.
right? So second breakaway point is not possible as clear from the sketch, as it is clear from the sketch. Hence we conclude that not all the roots of the equation dk is equal to 0 will be actually the breakaway points of the system, right? Only those points, only those roots of this particular equation dk is equal to 0 at which the angle criterion will be satisfied, only those points will be the breakaway points for that particular system. Am I clear? Because what is the definition of breakaway point? Or points at breakaway points, multiple roots of the characteristic equation occur. Multiple roots of the characteristic equations are located, right? So that means breakaway points are on locus points. Breakaway points will always lie on the root locus, right? So at the breakaway points, angle criterion will be satisfied. Is that clear? Is it clear? Yes or no?
Yes, ma'am. Yes, ma'am.
Okay. So our conclusion is from this example, we can generalize this particular example, and we conclude that not all the roots of the equation dk is equal to 0 will be the breakaway points. Only those roots at which the angle criterion will be satisfied will be the breakaway points for the system. So here again we look at this particular system. So you see this is one onlocus point, and this root which is minus 0.423, this root is indeed lying on this particular onlocus segment, right? So this at this particular point the system will have multiple roots, and yes, this is the breakaway point for the system. And what is the other root? I guess it's something like minus 1.5, something like that, isn't it? It's approximately minus 1.5, and minus 1.5, that point is located on this particular segment. This is minus 1 and this is minus 2. So the point will be located somewhere over here. And you see this segment is not on locus segment. That means at a point on this particular segment, the angle criterion will not be satisfied. Okay, so minus 1.5, that will not be a breakaway point for this particular system. So if the roots of dkds equal to 0 are real, then very easily just checking whether the segment on which the point is lying, that segment is one onlooker segment or not, we can verify or we can check the angle criterion, and accordingly we can decide which roots of the equation dkts equal to 0 will be the breakaway point or points of the system. Is that clear? Yes or no? Is it clear?
Yes, ma'am.
Yes, ma'am.
Okay. Now, just like real root, complex conjugate root pair also can have multiplicity of the order greater than 1, right? So on the S plane, complex conjugate root pair, follow the cursor, complex conjugate root pair with multiplicity greater than 1 can occur. So, as per definition, in that case, the breakaway point will be complex conjugate pair. Clear? Clear?
Yes, ma'am.
Now, for if you find that the solutions of this particular equation is complex conjugate pair, then just like real root, you won't be able to find out you'll not be able to apply angle criterion in a straightforward manner, right? So what we'll have to do, take any root, any complex root, and apply, construct the phasor, all the phasors, and apply angle criterion. So if you find that yes, at that particular root the angle criterion is being satisfied, then the conclusion will be yes, that point will be a complex breakaway point, and because of symmetry, because of the property of symmetry, the conjugate pair of that particular point will also be the second breakaway point, and we don't have to check because of the property of symmetry. At that particular point also, the angle criterion will be satisfied, right? So if the roots come out to be complex conjugate pair, roots of this equation come out to be complex conjugate pair, then at one particular root you'll have to apply angle criterion, and you'll have to check whether the angle criterion is being satisfied or not, and accordingly you'll be able to decide upon the fact that whether those complex conjugate root pair of this equation are complex conjugate breakaway points or not. Now, breakaway point has got one geometric interpretation. What is that? The breakaway point can be found from this particular equation dk ds equal to 0. Now, on the real axis, this argument is valid only on the real axis. So on the real axis, S comes out to be equal to sigma, only sigma. Otherwise, S equal to sigma plus j omega. On the real axis, S will reduce to sigma, right? So on the real axis, this equation will reduce to dk d sigma equal to 0. So far, is this clear? So far, is this clear?
Yes, ma'am.
Yes, ma'am.
So dk d sigma equal to 0, right? So that means k is being extremized with respect to sigma, isn't it? dk ds equal to 0. Either k will be maximized or k will be minimized. You get my point?
Yes, ma'am.
So dk d sigma equal to 0 means on the real axis at the Bricker points, the value of k will be extremized, either maximized or minimized. Uh, Let me go back to the previous figure. So let's take this particular example. So along this direction, k is increasing. At this particular point, at the open loop pole, the value of gain k is equal to 0 at this point. At this open loop pole, the value of gain k is 0, and the value of gain k is increasing in this particular direction, as well as the value of gain k is increasing along this direction, right? And at this particular real breakaway point on the real axis, the value of gain k is maximum, isn't it? On the real axis. Do you agree?
Yes, ma'am.
Okay. So if we take this particular example, then we find that when two real root branches are approaching each other and meeting at a point on the real axis, then at that particular breaker point on the real axis, the value of gain k will be maximum. And if we increase the value of gain k beyond this value, then those two real root branches will break away from each other and will form two complex conjugate root branches. Now let us discuss another example. Another example, this one. So these two are the two complex conjugate open loop pole pair, and this is the open loop. Sorry, this one is the open loop 0, located at is equal to -2, and the complex conjugate open loop poles are located at is equal to -1 plus minus j1, right? So we know that two root branches will originate from these two complex conjugate open loop poles. So since these two are the complex conjugate open loop poles, hence intuitively we can say that the two root branches which will originate from this complex conjugate uh, poles will be initially complex conjugate root branches. And if you sketch the root locus, applying all those rules that we have discussed, you'll find that yes, these are the two complex conjugate root branches, right? And at this point, if you solve for this particular system, uh, if you solve for the breakaway point, you'll find that at this particular point, multiple roots or two roots of the characteristic equation will occur, and hence it's generally called breakaway point. But to be more precise, actually this point is called break-in point. Break-in point. Why? Because here you see two complex conjugate root branches are approaching each other, and they are meeting at a point on the real axis, and after that you see one root branch will traverse along this direction and will terminate onto this open loop 0, right? And similarly, the second root branch will tend towards infinity. Here you see number of asymptotes will be 2 minus 1 equal to 1. So this root branch will tend towards infinity as k tends to infinity along the negative real axis. And this segment, this infinite length segment, is one on Locus segment. So why do we call this point to be a break-in point instead of breakaway point? Here, two complex conjugate root branches are approaching each other and they are meeting at a point on the real axis, and after that, they are forming two real root branches. That is the difference. In case of breakaway point, we saw that two real root branches uh, met at a particular point on the real axis, and after that, they form two complex conjugate root branches. The situation is just the reverse, just the opposite in this case. Here, two complex conjugate root branches are approaching each other. So, at this point, you see, suppose the value of gain k is some k1 equal to k1, right? So if you move along this direction, then it's clear that the value of gain k is increasing, and actually along this direction, the value of gain k is increasing towards infinity. Similarly, if you move along this direction, along this real root branch, then also you will find that the value of gain k is increasing and it's increasing towards infinity. Okay, so at this point on the real axis, it's a break-in point. So at this point on the real axis, the value of gain k is minimum. Do you agree?
Yes, ma'am.
Hence, we have justified the equation dkds equal to 0, and complex breakaway point. And let's take this example: GSHS is equal to k by s into s plus 4 into s square plus 4s plus 20. Again, I am not discussing all the rules, and again, I am not discussing the complete sketch of this, um, our complete Rootlooker sketch for this particular system. This is your assignment. Please draw the complete Rootlooker sketch for this particular system. Uh, but from this open loop transfer function, we find that the roots are four roots are there. Four open loop poles are there. Sorry, and the open loop poles are located at s equal to 0, s equal to minus 4, and s equal to 2 plus minus j4. Right. So to sketch the root locus, first of all, we'll have to place the these are the rules used for sketching the root locus, right? So we'll have to place the open loop poles. Number of open loops 0, in this case is 0. So two poles are located at s equal to 0 and s equal to minus 4. Other two are two complex conjugate open loop poles located at minus 2 plus minus j4, right? So if you solve the equation dkds equal to 0, yes, so k will be equal to minus s into s plus 4 into s square plus 4s plus 20. And if you solve this equation, you will have to do it. This is your assignment. So dkds is this one equal to 0. And the roots, I don't know whether the roots are correct or not, whether these values are correct or not, that we'll have to check. So apparently the roots of this equation are located at minus 2 and two complex conjugate roots located at minus 2 plus minus j 2.45. So since two roots are complex conjugate, so in a straightforward manner, directly you cannot conclude about the fact that whether the annual criterion is being satisfied or not. So take any point, either minus 2 plus j 2.45 or minus 2 minus j 2.45, construct the phasor and find out the angle. Find out the angle contributed by all the open loop poles and zeros at that. In this case, no zero is there. So by all the open loop poles at this particular point, and if the angle comes out to be equal to odd multiple of 180-degree, then this point will be a breakaway point. So if you apply angle criteria, you will find that yes, this point will be one on locus point, hence the conjugate point will also be one on locus point, and these two roots will be two breakaway points. So in this case, we'll get, if you sketch the root locus, we'll find that we'll get three breakaway points. So one root branch will originate from this open loop pole. The second one will originate from this open loop pole. The third root branch, just try to recall that the system is a fourth order system. So four root branches will be there. So the third root branch will originate from this open loop pole, and the fourth one will originate from this open loop pole, right? So these two real root branch will approach each other and they will meet at this particular point, which is minus 2, one root, the real root of the equation dkd is equal to 0. So they will meet at this particular point, and if you increase the value of gain k beyond that, then these two root branches will break away from this particular point and they will form these two complex root branches. Okay, so this at is equal to minus 2 will get two repeated roots of the characteristic equation. So now one root branch, complex root branch, is moving in this particular direction, and this root branch, which originated from this open loop pole, is now moving in this particular direction. So at a particular point, at this complex point, the location of which is at s equal to minus 2 plus j 2.45. So at this particular point, these two root branches will again meet. These two complex root branches will again meet. Hence, at this point again, we'll get two repeated complex roots of the characteristic equation. So after meeting at this point, these two root branches will break away from each other, and here number of asymptotes will be equal to 4. Okay, number of open loop poles 4, number of open loop 0 is equal to 0. Hence n minus n is equal to 4. So these are the asymptotes having angles 45 degree, 135 degree, 225 degree, and 315 degree. So these are the four asymptotes. So these two root branches will tend towards infinity in this direction. This root branch will tend towards infinity in this direction. Similarly, its conjugate pair, the conjugate pair of this point will also be a complex breakaway point. So you see this root branch is now approaching in this direction. This root branch originated from this particular point will move along this direction, and again they will meet at this point, and the point is located at s equal to minus 2 minus j 2.45. This is a third breakaway point, right? So after meeting, if we increase the value of gain k beyond the value of gain k at this point, then again these two root branches will break away from each other. One will move towards infinity along this straight line asymptote, as you can see, and the last root branch will tend towards infinity as k tends to infinity along this straight line asymptote, right? So apply all the rules that you have learned and sketch the root locus for this particular system. Now the question is, how could we say that yes, this root branch, this complex root branch which is originating from this complex open loop pole will move in this particular direction? Because you'll see in the previous example, so for this case also you'll have to sketch the complete root locus plot. So here you see the root branch that originated from this open loop pole complex. It's also a complex open loop pole. So the root branch originated from this open loop pole, but it moved like this in this direction. Probably this angle will be probably this angle will be 135 degree. But in this case, we see that this complex root branch originating from a complex open loop pole is moving in this direction. That means this angle is minus 90, right? So how to find out that in which direction, particularly for a complex open loop pole, how to find out in which direction the complex root branch will originate and will move, at least will move initially. Am I clear?
Yes, ma'am.
So whether the root branch which is originating from this complex open loop pole will move in this direction, or will be like this, or will be like this, how that can be ascertained? Okay, breakaway direction. I forgot to mention this one. Yes, the root locus, the example that we have discussed, in those examples, we saw that two root branches were approaching each other, and after that they were meeting at a point, and after that they are breaking away. And the breakaway direction is, you see, plus minus 90 degree. Why? Because the breakaway direction is given by plus minus 180 degree by r. So what is this r? R is the number of root branches which are approaching each other and meeting at a point. Am I clear?
Yes, ma'am.
So in this case, you see the value of r is equal to 2. Two root branches are approaching each other. Hence, the breakaway direction will be plus minus 90. Here also you see the initial breakaway direction. Two root branches are approaching each other, and the initial breakaway direction is plus minus 90. Clear? The breakaway direction is plus minus 90 degree. Clear?
Yes, ma'am.
So we can generalize this, and the rule is like this: if r number of root branches approach each other and they meet at a point, which is a breakaway point, then the breakaway direction will be given by plus minus 180 degree by r, and at that particular point, the root of the characteristic equation will have an order of multiplicity which is equal to r. Where it is? Yes, this is the breakaway direction. Can you see this? Plus minus 180 degree by r. Now, just now we were discussing that if the open loop pole is a complex open loop pole, then how to find out in which direction the root branch will originate from that complex pole. Why we are bothered about this? And similarly, we are also bothered about the complex open loop zeros. Let's look at this particular. Okay, let's look at this particular figure, right? So this is one complex open loop pole, but this is located at the origin. This is the second open. Oh, what did I say? Did I say complex? Anyway, this is the one open loop pole which is located at origin. This is the second real open loop pole located at this particular point, and along with this two, we do have two complex conjugates open loop pole pair located at these 2 points. Right? Now, okay, this is one open loop real zero, right? So it's obvious that one real root branch will originate from this open loop pole, one real root branch will originate from this open loop pole, right? This is one on locus segment. Okay, this is one not on locus segment. Again, this one will be one on locus segment, as and I can say that there is another open loop pole located at this particular point. So the this is one on locus segment. So one root branch will originate from this open loop pole as well. Now you see the root branch which is originating from this real open loop pole is doing so with an angle which is equal to this angle. This is the angle, right? So what is the angle? The angle is 180, isn't it? Yes or no?
Yes, ma'am.
Similarly, the root branch which will originate from this open loop pole will do so with an angle which is 0 degree. Yes or no?
Yes, ma'am.
Similarly, if this root branch terminates onto this real open loop 0, then it will do so with an angle which is 0 degree. So now we can generalize this that the root branches which will originate from real open loop poles will do so either with an angle which is 180 degree or with an angle which is 0 degree. Similarly, root branches which will terminate onto real open loop 0 will do so with an angle which is 0 degree or 180 degree. Is that clear? Is that clear?
Yes, ma'am.
Yes, ma'am.
But for complex open loop poles, we don't know. The root branch can originate like this, the root branch can originate like this. Already we have seen two cases. So, for complex open loop poles, we'll have to find out the angle along which the root branch will originate from it. And that angle is called angle of departure. Okay. So, with which angle the root branch will depart from one complex open loop pole. So if you can find out the angle of departure for this open loop pole, you don't have to compute the angle of departure for this conjugate open loop pole, because of the property of symmetry, you can very easily find out the direction along which the root branch will depart from this conjugate open loop pole. Similarly, angle of arrival at complex open loop zeros. So for complex open loop zeros, again we'll have to find out the angle of arrival. For complex open loop poles, the angle is called angle of departure. The root branch is departing. And for complex open loop zeros, the root branches are arriving at the zeros. Hence, the angle is called the angle of arrival. Have you understood this? Have you understood this? Please respond.
Yes, ma'am. Understood.
Okay. Again, we'll refer to this figure, right? Now, let us assume that this is the open loop pole zero configuration for a given system. So here we are having three real open loop poles, two complex conjugate pole pair, and one single real open loop zero. Now, to find out the angle of departure from this complex open loop pole, so it's obvious that for real open loop poles, we don't have to compute the angle of departures, because the angle of departure will be either 0 or 180 degree, and that will be obvious if you can find out the onlookers and not onlooker segments. Similarly, angle of arrival or angle of arrivals for real open loop zeros, uh, for that we don't have to extensively compute the angle of arrivals, as the angle of arrivals will be either 0 or 180 degree. Yes, this example will help us in this regard. So you see, angle of departure in this case for this real open loop pole is 180 degree. The angle of departure for this real open loop pole, or from this real open loop pole, is 0 degree. And for this open loop pole, the angle of departure is 180 degree. For this open loop zero, you see the angle of arrival is 0 degree, and for this open loop zero, the angle of arrival is 180 degree. So for real open loop poles or zeros, angle of departures and angle of arrivals will be either 180 degree or 0 degree, right? But we'll have to find out angle of departure and angle of arrivals for complex open loop poles and zeros. So let's look at this particular diagram. Here we take a point S, which is one on locus point. That means this point S or S0, whatever, this point is lying on the root locus, and hence we can say that at this particular point the angle criterion is being satisfied, as it is one on locus point. And another assumption of this point about this point is that we assume that this point is very close to this complex open loop pole. So two assumptions. One is this point is very close to this complex open loop pole, and the point is one on locus point, right? Now we construct all these phases. So is 0 plus say P1, is 0 plus P2, is 0 plus P3 is 0 plus Z1 and is 0 plus P4, and this is the last phasor, and this is the complex open loop pole of concern, right? So at this particular point, let us find, write it down. The net angle contribution by all other open loop poles and zeros, excepting this particular complex open loop pole for which we want to find out the angle of departure. Here, so from this figure, you see these are the angles. This is theta 1, this is theta 2, this is theta 3, this is theta 4, this is theta 5. And this angle, the angle contributed by this complex open loop pole at this particular point, has been denoted by phi p. Phi p. Okay. So at this point, net angle contribution, listen carefully, net angle contribution by all other open loop poles and zeros, excepting this one, will be some phi. Write it down. Phi is equal to theta 4 minus theta 1 minus theta 2 minus theta 3 minus theta 5. Done?
Yes, ma'am.
So, at this particular point, which is very close to this complex open loop pole, the net angle contribution, now I'm using the term the net angle contribution by all the open loop poles and zeros will be phi minus phi p. This angle, phi
Yes,
was the
ma'am.
net angle contribution by all other open loop poles and zeros excepting this one. So net angle contribution by all the open loop poles and zeros at this point will be given by phi minus phi p, right? And since ace is 1 on locus point, then phi minus phi p will be equal to phi minus phi p will be equal to plus minus 180 degree 2q plus 1. Angle criterion will be satisfied at that particular point. Agree? Do you agree?
Yes, ma'am.
Yes, ma'am.
So from this equation we can write phi p is equal to plus minus 180 degree 2q plus 1 plus this one will be phi, not theta, plus phi. And what is phi? Again, I repeat, phi is the net angle contribution at that particular point by all other open loop poles and zeros excepting the complex pole for which we want to find out the angle of departure. Clear? This is our phi. Is this clear? Yes or no?
Yes, ma'am.
Okay. Now, what was our assumption? Second assumption, ace is very close to p. So in a limiting condition, if we assume that ace and this point, let's call it p, this point, these 2 points are same, right? These 2 points are co-located. These 2 points are identical. Initially, our assumption was S is very close to this particular point. Now, if we assume that very close, so in the limiting condition, we can say that these 2 points are identical. If that be the case, then this phi p will be the angle of departure from this complex open loop pole. Have you understood the logic?
হ্যাঁ ম্যাম বুঝেছি।
বোঝা গেছে? So the next rule is the angle of departure from an open loop pole is given by phi p, angle of departure, equal to plus minus 180 degree 2q plus 1 plus phi, where phi is the net angle contribution at this pole by all other open loop poles and zeros. And similarly, we can derive the expression for angle of arrival at an open loop 0. Only the difference will be in this case when we'll be calculating the net angle. The angle of arrival is denoted by phi z, and phi z will appear with a positive sign because phi z will be the angle contributed by a complex open loop 0. So this one will become phi plus phi z, and hence the second part of the rule is similarly the angle of arrival at an open loop 0. Open loop 0 is given by phi z, which is equal to plus minus 180 degree 2q plus 1 minus phi. Again, phi is the net angle contribution at the 0 under consideration by all other open loop poles and zeros. And already we have discussed this. It easily follows from the rule or from any sketch that the angle of departure from a real open loop pole or angle of arrival at a real open loop 0 is always 0 or 180 degree, right? So angle of departure should be calculated for complex open loop poles, or angle of arrival should be computed for complex open loop zeros. So here is one example. Calculate, the angle is shown. Calculate the angle of departure. So two open loop poles located at -1 plus minus j1, and one open loop 0 located at -2. This is -2. So calculate the angle of departure for this complex open loop pole. Do it fast. Do it fast. I do have a meeting from 8 p.m. I'll have to finish with Lucas technique. Today I'll have to finish with Lucas technique. Please do it fast. Okay, got this value 135 degree. Got this value? Yes or no? Hello, please respond. Hello, can you hear me? Can you hear me? Can you hear me? Yes or no? Please respond. Can you hear me? Hello? Yes. Yes. So please do respond. So anyways, the angle as you can see is 135 degrees. So this root branch will originate like this, and because of the property of symmetry, this root branch will originate like this, right? So for this particular example, if you calculate the angle of departure from this particular complex open loop pole, you'll find that the angle of departure will be minus 90 degree. And already we have discussed the example for which we have computed the angle of uh, departure. So this is the root branch, and you see that the initial angle with which the root branch is departing this complex open loop pole is 135 degree. Hence, if we calculate complex angle of departure uh, or angle of departures for complex open loop poles, then we'll be able to guess the initial path of the root branches, complex root branches. And next is the last rule. I guess I've discussed this one. Yes, this example. Do you see that for a certain value of gain k, two root branches are intersecting with the imaginary axis, right? So that means for that particular value of gain k, the system will be a limitedly stable one, right? Whatever be the value of gain k, two roots of the characteristic equation will lie in the left half of the S plane. One is on this root branch, the other one is on this root branch. So always two roots of the characteristic equation will lie in the left half of the S plane, but after a certain value of gain k, you see two root branches are moving in the right half of the S plane. So for those values of gain k, two roots of the characteristic equation will appear in the right half of the S-plane, thus making the system unstable. So again, we'll have to find out the range of gain k for which the system is stable, and we know how to find out the range of gain k for which the system will remain stable. How? By applying Raoult's stability criterion. So this is the rule, last rule. The intersection of root locus branches with the imaginary axis can be computed by using Raoult's criterion. So let's take that particular example where the open loop transfer function is given by k by s into s plus 4 s square plus 4s plus 20. So for applying Raoult's stability criterion from open loop transfer function, we'll have to formulate the characteristic equation. So this is the characteristic equation. This plus k is equal to 0, right? Now we'll apply Raoult's stability criterion. So it's a fourth order system. So the first row will correspond to a term which is s to the power 4, and the elements are, please do check, elements will be 1 plus 36 plus k, 136k, and the second row will correspond to a term s cube, and the elements of that particular row will be 8 and 80. So 8 and 80. So they have divided the elements of this row by 8. So now the new elements of the this row corresponding to s cube are 1 and 10. So if you compute this table, if you complete this table, you'll find these elements which are appearing in the first column of route array, and we know that for the stability of the system, all these elements should be greater than 0. So that means k should be greater than 0, right? And 260 minus k should be greater than 0. That means the limiting value of gain k is 260. 260. So if the value of gain k is 260, that is the limiting value. So for that particular value of gain k, the system will be limitedly stable, and hence this term will become 0. So S1, this row will contain all 0 terms, right? So with this elements, we can form the auxiliary equation, and the auxiliary equation will be given by 26 s square plus k is equal to 0. Okay, so we can solve this, and we find that for a value of gain k equal to 260, the roots of the characteristic equation, two roots of the characteristic equation will be on the imaginary axis, hence the system will be limitedly stable, and will be, the roots are located at plus minus j root 10, right? So if you increase the value of gain k beyond 260-degree, then two root branches will move in the right half of the S-plane, or in other words, two roots of the characteristic equation. Out of four roots, two roots of the characteristic equation will appear in the right half of the S-plane, and hence the system will be unstable. And for this value, since the system is limitedly stable, it will exhibit undamped oscillation at its output, and the frequency of the undamped oscillation will be root 10 radian per second. Clear? So these table actually provides the uh, rules for constructing the approximate root locus for given LTI system. And this is the last rule. Already we have seen this magnitude criterion. From magnitude criterion, we can find out the value of gain k at a particular point on the root locus. So if the point of concern on the root locus is 0, then the value of gain k can be obtained using magnitude criterion, and the value of gain k will be product of phasor lengths from S0 to all open loop poles divided by product of phasor lengths from S0 to open loop, all open loop zeros. Clear? So this is another example. That is your assignment. Construct the complete root locus for this given system whose transfer function, open loop transfer function, is given by this. So do you have any question? Do you have any question? Since I'm not getting any response, so I'm closing this file. Abid Hassan has raised a hand. Yes? Do you have any question? Just a moment. Let me stop the recording.